equations. So what happens is this gives me a set of, when I solve this, I get some lines or some curves. And when I solve this, I get some curves. These curves, I'll just draw some. I might get a curve that looks like that, and another one that looks like that. So this is the line fxy equals 0. This is also the line fxy equals 0. Here I get a curve that comes from the relationship gxy equals 0. Here I get another curve, gxy equals 0. So I'm drawing the case where these give me some lines. There may be 1 line, 2 lines, 3 lines. But the important thing to note is where both are 0. So both are 0 at this point and at this point. So where the red lines and the blue lines intersect, that's where both fxy and gxy are 0. So what are those points? What do I call those points? Both of these are 0. So I look at them one at a time, and I get lines, but when both are 0, I call it what? The equilibria. So where these intersect is where you get your equilibria. So the way to analyze these graphically is to draw the isoclines and see where they intersect. And these isoclines, because I'm drawing them at equal to 0, I can draw them for any constant, but I'm drawing them at 0, I call them nullclines. Now if I go to a model of this form, the x dt equals x times fxy, and dy dt equals y times gxy, then as opposed to a model like this, where I'm saying I have a total growth rate, now what I have is that f and the g represent a per capita growth rate. So this is a good model for populations that are growing. This is a more general model in mathematics. But once I do it like this, and I write it down like this, the implication is that I really have a model with a per capita growth rate, where the per capita growth rate depends on both variables. And in this case, if I look at the nullclines are either x equals 0 or fxy equals 0. And these are the x nullclines. And the y nullclines are y equals 0 or gxy equals 0. And in this form, you see that if I'm writing it in terms of per capita growth rate, then it says that whenever the population is 0, it can't grow. So kind of there's no spontaneous growth. Now, you might say that there couldn't be spontaneous growth in any population. But in fact, if you had an area and you said there was migration in and out, you could have nothing there and a migrant could come in. So not all models of populations can be put in this form. So if you've got migration and the individuals that are coming in do not depend on the number of individuals there, then you wouldn't be able to write it down in that form. But if you can write it down in this form, then it's actually a little simpler than just looking at it like this, because you immediately see that there's a factor x and a factor y in the first and second equations. And so when you look for the nullclines and the equilibria, so this tells you that x equals 0 and y equals 0 is an equilibrium. Or there's an equilibrium with x equals 0 and this equation if they intersect. Or an equilibrium with y equals 0 and this equation if they intersect. Or if these two intersect, then what you would say, this is a non-trivial equilibrium, because if they intersect, they're doing so where x and y are not 0. So where x and y are 0 is called a trivial equilibrium, and where x and y are not equal 0 is some kind of non-trivial, or actually you can call it a coexistence equilibrium, because at that point both populations can coexist as an equilibrium. The equilibrium might be stable or unstable. If it's unstable, then some interesting things are going to happen, and one of the populations may go to 0, or the other population may go to 0. Or if it's not a very good model, one of the populations may grow without bound. So it's like the exponential model we decided was not a good model because it could predict that the population would grow without bound. And we said that's no good, so what we did is we added a per capita growth rate that had some density dependent in it, so we turned the exponential into the logistic. Okay, so let's have a look at some of the sorts of things that can arise. So a phase space, and in this case the space is a plane, xy, is what we call the plane in which we do this analysis. For historical reasons, it's called a phase plane. I don't want to explain why that's... The reason why that's done, actually, is because the first analyses that were done in this context were done in electrical current theory, and people used polar coordinates. How many of you know what polar coordinates are? Okay, so polar coordinates, if you look at the plane, any point in the plane can be written either in terms of x and y, or it can be written in terms of r and theta. If it's written in terms of r and theta, then this is r, the distance from the origin, and this is theta, the angle from this positive axis. And x and y and r and theta are related through trigonometric functions. If you remember that, you can say x is r cos theta, and y is r sine theta. Or you could express r and theta. If you remember, r is x squared plus y squared to the square root, or theta is the tangent of y over x. So you can have x and y, or r and theta, whatever. And it was called a phase plane because the analysis of these electrical systems was done in terms of r theta coordinates rather than x, y. So that's just a historical reason. Now, when we talk about models of the form dx dt equals x times f of xy, and dy dt equals y times little g of xy, per capita growth rates, generally we're interested in the positive quadrant. The positive quadrant, because we're interpreting x and y as population densities. And so x and y, it only makes sense to have non-negative values for x and y. It can either be 0 or positive, but you can't have a negative population. But there may be other systems, like electrical systems, where you can have x representing the amount of current in the positive direction, you can get current in the negative direction. So there are other systems where you might do it in the whole plane. But when we're talking about population systems, this is generally the case. And so the nullclines are either where x equals 0, or f equals 0, or y equals 0, or g equals 0. And let me make this a little bigger. And so you can plot these curves, either x equals 0, or f equals 0, g equals 0, or y equals 0, and g. So I've done the nullclines for x, for the equation x in red, and the nullclines for the equation in y in blue. And where they intersect, where red and blue intersect, is where you get the equilibria. So here you get an equilibrium here. This is the trivial one. Here you get two non-trivial equilibria, if it looked like this. These are complicated curves. Generally, in the examples that we're going to look at, you won't get complicated curves like this. But this is a general situation. And then you can say, if this is the line where f is equal to 0, then you can say below this line, f is positive, and above this line, f is negative. Or it may be the other way around. But one of these two cases will apply. If this is separating out f from positive and negative, then this is, one side is positive, one side is negative. So let's assume that the top side is negative and the bottom side is positive. That's the red. This blue line separates out where g is positive or g is negative, because along this blue line, g is 0. So let's say below the blue line, g is positive, and above the blue line, g is negative. This means when you below both lines, f is positive and g is positive, so both populations are growing. So that means x is increasing and y is increasing. If you're over here, this blue line is where g is separated. So below here, g is positive, above here, g is negative, but we're still below the red line where f is positive. So if f is positive, it means x is growing, but y is decreasing, so the population must be going in that direction. So each one of these areas you can fill in with arrows. And so it tells you if you're at an arbitrary point in here, this is where f and g are both positive, so both populations are growing. As they approach this line, this is the line where f is not changing. This is f equal to 0. So that means x is not changing on this line, but y is still growing. So that means we must be crossing that line vertically. If you come to this blue line, on this blue line, f is not changing. This blue line is g is 0, so y is not changing, but x is. And we're below this red line over here, so it means x is growing, but y is not changing, so we have to cross this horizontally like that. So it means that if you start out, you've got to move like this, you've got to move like this, and you can see you're kind of winding into this point. If you're close to this point, you can show that you move away and you head over here. And so if you can plot all these arrows out, you can understand where the population is going to grow, where it's going to go to. So this is a qualitative analysis. Now this is particularly complicated. The models that I'm going to work with are going to be much simpler than this. But in general, this is why a phase plane analysis is useful, is because you can map out directions of where the population system, the two populations are going to go. Are they both increasing? Is one increasing and one decreasing? You can take these different regions and say, what is it doing there? And then if you trace points, you can say, okay, it's got to be behaving like this. It has to cross the blue line horizontally, and it has to cross the red line vertically. And so how would it move around in the space? And immediately when we look at this, we can say that this is an equilibrium that it oscillates around. Here we've got an equilibrium that it goes to. Here's an equilibrium that it goes away from. This is an equilibrium that if we're on this side, we go down to here. But if we're on this side, we head up to here. So this is kind of separates out the points into solutions that end up down here or solutions that end up over here. So this is called the separatrix, because it separates the plane into points that if you start out on one side of the separatrix, you end up in one equilibrium. And if you start up on another side, you end up in another equilibrium. So I'm kind of giving you this broad general overview so you can understand what kinds of things can happen. But what we'll do is we'll look at competition processes and pre-predict processes using this approach, and then we'll understand how these systems behave. And as I said, in order to get something that looks like this, it means that the right-hand sides of the equations, fxy and yxy, must be complex polynomials or complex functions. But most of the things we're going to deal with are going to be rather simple. So this is just a picture of a more complicated system in general, but the system that we work with will be simpler. And for example, prey-predator systems. So prey-predator systems, you can go to Wikipedia, and the initial study of prey-predator systems, two mathematicians independently looked at these systems, and then they saw that they had such similar work that they, let's see if we can open this, it's not opening, that Locke and Volterra, that their approach became a classic. And what they were doing was they noticed that there were certain systems where populations would oscillate. Volterra looked at, he was in Italy, and in the fisheries, he noticed that in some years one species was abundantly caught, and in other years another species was abundantly caught, and the catch oscillated between these two species. They tried to explain this oscillation, and he said these fish, ecologically, these two species had a prey-predator relationship that caused these oscillations. Then there's a classical data set called the lynx hare data set. In Hudson Bay, fur trappers would either they could get lynx or snowshoe hare fur that they would sell. In some years, there were a lot of snowshoe hare and very few lynx. In some years, there were more lynx and fewer snowshoe hare. And so if you look at records on the number of pelts that were sold of these two species, they have these oscillations. So one of the things that ecologists first try to understand is, why do you have oscillations? And what they found out is that the lynx snowshoe hare kind of oscillated roughly on an 8 to 11 year cycle. So they'd be down, and then 8 to 11 years later, they would be up, 8 to 11 years later, down again, or whatever. So actually, from one low to the next low is 8 to 11 years. From one high to the next high is 8 to 11 years. that defined the cycle, and they wondered why that would be. And so this led to modeling the system using equations that have come to be known as prey-predator equations, or more specifically, Lotka-Volterra equations. So that's the historic situation. What they did is they wrote down an equation that said, if X is the prey, then the per capita growth rate would be a constant unless Y is there, the predator, in which case the per capita growth rate goes down with Y. So it's a very simple model. They said the predator, in the absence of the prey, would decline exponentially. There's not enough food to just decline exponentially. However, if the prey are there, then they would increase in proportion to the amount of prey. And so the per capita growth rate would look something like this. If you then plot the null clines for this, you find that either x equals 0 or y equals ab are the x clines, or y equals 0 and x equals cd are the y clines. So you get a diagram like this, and you get an equilibrium there and an equilibrium there. And if you plot the arrows, as I talked about, you'll see that it's a very simple diagram, and you just go round and round. And if you take Nova and you simulate these equations, you'll see that they go on trajectories like this. They don't look like circles, they don't look like ellipses, they look like these rather flattened ovoids that go way down over here, and then the prey population is at a low density, and all of a sudden it breaks out. And so you get these outbreaks of the prey. And then what happens is the prey breaks out, the predators now got lots of food, they grow. Eventually you've got so many predators that they cause the prey population to crash. And it takes time to recover again. And if you do that, you get cycles that looks like this. And again, you can simulate this in Nova. And if you go to the calculus textbook 8.5, example 1, then it'll discuss how to draw the isoclines and how to analyze the behavior. So that's it for today. And then coming next, on Thursday, we're going to discuss the prey-predator system in more detail. And so I'll see you all on Thursday. And again, I'm sorry that I'm not going to be around tomorrow, but if anyone wants to see me early Thursday morning, then just send me an email and I can meet you from 8 o'clock onwards. By the way, did anybody see a power cord? I've lost my power cord for a Mac.